Okay, let's go ahead and start the class. AESP. So there was a problem with the recording of Thursday's lecture. So it didn't have any audio. Some of you have tried listening and watching the lecture online. But I guess it doesn't have any audio. It is not going to make any sense, right? So because of this, I'm going to change the due dates, extend the homework to extend it another week. But at the same time, I'm going to post the other homework, the next one, which is going to be due the next Thursday, right? Not the upcoming Thursday, the Thursday next week. Both of them will be due at the same time. I'll try to make this third homework a little shorter, right? I mean, the material we are going to cover is itself just a couple of explanatory questions. I can't really think of any problem that I can give you to solve, right? Yes.
The homework, we can just do everything on MATLAB that can be done on MATLAB. We don't have to do it out by hand, right?
So we were just talking about it. So for the homework that was posted, I think on Saturday, right? Which is homework 2, right? First question, you need to use MATLAB or any other software. That doesn't really matter to me. I should be able to compile the code, to run the code. That's it, right? So I know Python, C++, Java, MATLAB, what else? Fortran. So as long as it is one of these 4, you should be fine. I should be able to understand what you have written, right? And I don't think my TA does know this material, so I'll probably grade this first part myself. Second question, you have to do by hand, right? Because it's a 4th order differential equation, and you have to transform it to a first order or ordinary differential equation, a system of first order, and it is done by hand. It's pretty simple. We have gone over it in the class. You should be able to do it. It is a very simple thing to do. And the third part, you just have to take the M files that I've uploaded and explain what each line of code does, right? So I expect to see 1 comment for each line of code, right? That's it. And the purpose of this is for you to understand how this code is written in your book, right? As they have made it a little more complicated because they wanted to use the functions they define here in elsewhere as well, right? So we may use these later on, and I'm not going to go over the function. I just want to make sure that you understand these, right? Yes?
Since it also does call back to the other 2 functions, does that mean that we need to explain within those functions?
Yeah, so you have to explain all M files that I have uploaded, not just the one. There are 3 M files that are uploaded. Just have to go over them and explain what each line does. The best way to do this is to just make sure you can run the code yourself. There may be some bugs. The first time I ran them, there were some bugs. I had to fix them myself, but I gave you the original code. So there is probably 1 bug at least, right? It's pretty easy to fix. You just have to change 1 name, right? I may have given you the corrected version. I don't remember. But yeah, if there was a bug, try to fix it and make sure the code runs. Then you can go step by step and see what each part of the code does, right? Any questions? Yes.
Is the homework graded just out of 2 points?
Yes. It is out of 2 points, yeah.
So a 2 out of 2 would just be 100.
Yes, exactly. So you may have received your first homework grades already. It is out of 2. All homework, any exams or homework are going to be graded out of their proportion of the final exam. So if exam 1 of final grade, if exam 1 is 20% of the final grade, your exam 1 will be out of 20, right? So don't freak out if you see it like 1 out of 2 on a homework. This is 1 out of 2, right? I mean, 1 is not a very good grade because it is 50%, right? But don't freak out. It is still good enough. Any questions? Okay, yes.
Will we be able to see like corrections from what we did wrong on the homework?
She was supposed to put some brief comments, right? So you should have received some comments on your homework. But if not, then you come to me, I'll talk to her and give you her comment. If I see she has made a mistake, I will, of course, correct the mistake. But the weight of the homework is like 22%, so I don't really want to focus that much on that. And I've told her to be lenient with the grades. So she probably has given you more than what you deserved. Okay? I mean, I didn't mean it a bad way, but I mean, she is supposed to be lenient with the homework grade, right? But she may have made a mistake, so it is possible. So if you have a question, make sure to reach out to me. And yeah, that's it. Okay. What else? Your other homework is going to be uploaded on Thursday, hopefully. And it will have 1 or 2 questions, probably just simple problems or explanations, because most of the things that we are going to go over this week are just introductions to the terminology, right? And what each concept is. It is going to get a little confusing because we have a lot of different coordinate systems that we are going to introduce, but the mathematics of it is pretty easy, right? And there are a lot of you who have sent me an email with a positive COVID test. They've told me that you have, and most of these people are not in class. All of them are not in class. If you have a positive COVID test, if you have any sort of symptoms, don't come to class. Just send me an email. Don't come to class, right? The lectures are uploaded. Hopefully, I'm going to continue uploading them every week. And you can always come to my office during the office hours or any other time and ask your questions, right? So if you have symptoms, don't come to class. If you have this, like the smallest of symptoms, don't come to class, because we don't want to spread any kind of disease, not just the COVID. And it is not going to be held against you not coming to class because of, in general, not coming to class is not going to be held against you. So. For any reason. Any questions? No? Okay. So let's start the class. This is going to be the first lecture of the flight mechanics part of class. During the past 2 weeks, we went over into a review of dynamics, essentially, and what parts of the dynamics that we are going to use in this class. And we are going to essentially start the first part of the class, flight mechanics, today. And this will go on until your first exam. So your first exam, which is going to be on March the 3rd, will have we'll go over the review and the flight mechanics part of the class. Hopefully we'll be able to finish the flight mechanics part of the class by the first exam. It is March the 3rd, the exam, right? Keep that in mind. Okay, so what do we want to do here? We are essentially going to talk about the mechanics of airplane flights. We are going to focus on the airplanes. Not a spacecraft, just airplanes. There are a couple of assumptions. What we are going to discuss here is that we are essentially going to talk about the performance of an aircraft. Specifically, we will talk about rate of climb, flight regimes, takeoff and landing performance, range and endurance, and turning rates. We will do a little bit of aerodynamics. If we have enough time, we will talk a little bit about propulsion, which is going to be just a review for those of you who have taken the propulsion course last semester, and introduction for those of you who are going to take the propulsion course next semester. What are the assumptions we are going to make here? We are going to assume that translational motion of the aircraft is due to all of the external forces that are applied to center of gravity. So first assumption, all forces are applied to center of gravity. Second assumption, we are going to assume Earth is non-rotating and flat. So flat Earth assumption. And the third assumption is that airplane is treated as a point mass. Which we have reviewed the dynamics of the point masses during the past 2 weeks. Okay. One thing that I was thinking about this, I forgot to mention. So the textbook we are going to use for this part of the class is Elements of Aircraft Performance and Introduction to Flight. I assume that you have used Introduction to Flight textbook for your AESP 101. If you have taken the AESP 101, or you definitely have to take it if you have not. So you are going to use this. So let's start. Again, we are going to become familiar with the terminology this week, mostly. And then we are going to use the equations and terminologies we learned this week, the upcoming weeks, to try to analyze rate of climb and all of those things we talked about. So first thing we need to become familiar with is center of gravity. Who can tell me what the center of gravity is?
It's basically the point of the body where all the, you can kind of imagine all the mass is pointing downward from all the weight or gravity points back downward.
Point of the body that weight is applied to, I guess. This sentence became a little crooked, but yeah. Hopefully you understand what I mean. So essentially, I have the official definition here as well, the point through which the resultant force of partial weights act, which is going to be independent of altitude, of the airplane, right? But how can we find this location? Let's say you have this plane. Not a very good drawing, but hopefully you get the point. You have you have these two planes, and then you can measure that. You have to put them on these scales. You can measure the resultant force, the reaction force, the normal force, N. You're gonna have, let's call this N1 and N2. And then you are going to measure the distance of N1 and N2 from the center of your coordinate system. Let's call this X1 and X2. Center of gravity, which is, let's call it X of G, is going to be the weighted average of these two. N1 X1 and 2 X2 divided by your weight. Again, we are just going to go over the terminology so that there won't be that much of a flow in the course. We'll jump from point to point. Force balance on an aircraft. So the forces that we have to deal with on an aircraft. Of course, we need to use the second law, which tells us that the total amount of forces are going to equal to your mass multiplied by acceleration, right? And acceleration, if you recall, is the second derivative of your position, right? So from the review we have had during the past 2 weeks, you remember that second derivative, since we are an aircraft that is moving, right? So we have a rotating frame, we have a moving frame. The second derivative is not that simple to deal with. It has different parts, right? It has a relative acceleration part, right? What are the other parts of it? Does anyone remember? You have the omega,
Omega dot. Omega cross omega r. Omega cross r.
r, right? Which is r here is your altitude plus Earth radius, right? Or let's call it z. Plus
Omega dot cross r.
omega dot cross r. Plus 2 omega e multiplied by your velocity, right? This is the general. It omega dot cross, it is hidden in the second term. This part, pardon me.
Is it one more term or is that?
These are the only terms that we are going to focus on. So this part for us is the Coriolis acceleration. If you recall, we are going to say A of C. This part is called A of T, or tangential acceleration. So on an airplane, F is going to be equal to your relative acceleration plus the tangential plus the Coriolis acceleration. This is something we have seen before. We also talked about the angles that we were dealing with. If you are on the Earth, your airplane is moving here, and you have the coordinate system. What did we call this angle? Theta. Latitude, right? The aircraft itself, the velocity, let's say this is the rotation axis, and we have this velocity in this direction. Aircraft itself makes an angle phi, which is again angle between the velocity vector and the axis of Earth. So two main angles here that we are dealing with: latitude and velocity and angle of Earth. Something that I should mention here, and most of the students get very confused here. The theta and phi that we use here are going to use later for different angles. So when you're dealing with the movement of a point around the Earth, whenever you hear theta in this book, Elements of Aircraft Performance, right? We use a different parameter when we are dealing with the dynamics of point masses. It is referring to the latitude. But when you are looking at it at a smaller level, the aircraft itself and its location to the air surface, then essentially you bring in the assumption that the Earth is flat, theta is going to mean a different thing. So make sure you are not confused. And if I was the author of this book, I would have used a different letter, I guess. But I'm just following what your book does. You probably need to use a different letter. Okay, any questions so far?
Let's go back and
Sure. Let's talk about one of the assumptions before moving on to the rest of coordinate system analysis. The curvature of the Earth. So we assumed the curvature of the Earth is negligible, right? This was one of the main assumptions when it comes to fluid mechanics. But why is this the case? Or where is the criteria? When is the point? Is it an altitude? Is it a density? Is it a velocity? After which we cannot assume Earth is flat. What do you think? Where is that criteria? Where is that breaking point? After which we cannot really assume Earth is flat.
Is it like a scale? How large is
A scale? A scale of what? What are you measuring on this scale?
Like, it would be a combination of how quickly your gravity and how high it is. Like, basically, how large is it you have to look at?
How quickly your aircraft is moving. Quick. Velocity. Let's call it velocity. Right? Or do you mean acceleration? Velocity then. And altitude, right? Yes.
Direction of travel.
Direction of travel. So, what else? Yes.
I don't know if this is true for this, but there's like the rule of small angles where you can almost approximate that it's flat if the angle is small enough.
So what you're saying is that theta is equal to tangent of theta, right? Is it what you're saying?
So there's a certain angle where that's no longer the case. And then you can assume.
So you're saying if the curvature is small enough, we can assume that it is not curved at all. So to answer the question, you have to go back a little bit, right? What is it that we have when we are moving around the curved surface that we don't have on a flat surface?
How gravity pulls us?
No, but we have the gravity in the curved surface. Yes.
You have like a normal component of your acceleration.
You have a centrifugal force, exactly. So centrifugal force is present here. That is not present on the flat Earth, right? Which one of these parameters contribute to the centrifugal force specifically? Direction, not really. This is a small angle assumption, not really. What about altitude? Altitude may, right? And also velocity, of course. So the curvature, both of them. If you recall, what was the centrifugal acceleration? Or the normal acceleration, how did we calculate this? V squared over rho, exactly, or over r, right? So altitude is important. So both of them are important. But let's come up with a criteria. And the criteria we are going to come up with is essentially is going to tell us whenever your centrifugal force is equal to your weight or higher than that, then you cannot really assume that Earth is flat. I mean, let me put it this way. If you are getting close to your weight, centrifugal force is getting close to your weight, then you cannot assume Earth is flat. And how can we find this? So let's actually put this. Centrifugal force is calculated by m theta dot or omega. This is mass. This m stands for mass. Cross theta dot. And again, I'm changing the letters used to fit the book, right? So this is omega or omega of Earth, right? Both of them are true. RE is the Earth radius, and H is your altitude. Is going to be equal to your weight, right? Of course, it's the scale version of the weight. So this force balance, we are saying if this force balance is true, then meaning that this part of it, the centrifugal part of your force, is equals to your weight, then the earth curvature becomes important. If you rewrite this, play with this a little bit, you can come up to this conclusion. I mean, we are making a lot of assumptions, but eventually this is going to be equal to v squared multiplied by the gravitational pull. Is that your centrifugal velocity is going to be equal to RE plus H. This is the centrifugal velocity multiplied by G.
Is that, C over omega or over
W.
W?
Yeah, wait. Okay, so if you make some calculations, you see for this velocity, if you like plug in the radius of Earth, which is 6,371 kilometers, and the gravitational pull of the Earth G naught, assume doesn't change with altitude, 9.8665 meters per second squared, then we can find this velocity to be 28,000. Give me a meter. Let me give you meters per second. This velocity, we can find it to be 77,904 meters per second, which is equal to 28,455 kilometers per hour. So, during regular flights, are we close to this speed? Not at all. What is the Mach number of this speed? Around 20, right? Because the speed of sound, we always assume is 343 meters per second. So this is close to 20 times 1/20th of this velocity. So as long as you are operating in Mach 7, 8, you can safely assume that Earth is flat, right? You're not getting close to that force that is going to pull. The centrifugal force is not going to be important. Yes?
So is that essentially escape velocity?
We will talk about the escape velocity later. Yeah. On the space part of the class. Yes.
In this equation, what are we assuming H to be?
Pardon me? H is your altitude.
Yeah, no, but like, do we put a physical number in there to obtain the
So no, on the surface, we are assuming that we are on the surface. So on the surface of there, as you go away from, because RE, we are assuming that H is negligible compared to RE. Okay, so Earth is flat. That is proven, right? Again. Let's move on. And this is the confusing part of the class that we are going to start. So I'm going to go very slowly, and please listen. Coordinate systems. Again, we are already familiar with the inertial coordinate systems that we put on the center of the Earth, and we are already familiar with the moving coordinate system that moves with the speed of the Earth, right? Rotates with the angular velocity of the Earth, right? And we are already familiar with the coordinate system that is going to lie on the surface of the Earth, right? So we are going to start from here and then come up with new coordinate systems that are going to characterize our flights and its relationship to the Earth's surface. Okay? Let's do that. So, first thing we want to learn here, first coordinate system, is the Earth axis system. What is an Earth axis system? It's a coordinate system that is on the surface of the Earth. I should give it a little more room here. On the surface of the Earth. Again, a flat Earth. It is x of, let's actually use a different, x of g y of g, and z of g is going to point inward. Again, this Earth axis system lies on the surface of the Earth. And we have the, let's assume this point is your plane. Then we are going to define another axis coordinate system. It's called moving Earth axis system. That is going to be parallel to your Earth axis system, but is going to sit on the airplane. So it's essentially the same system, but move to an altitude. Move to your aircraft. Next one is called the body axis system. Body axis system, I'm going to draw here. Let's say this is your aircraft, center of gravity. Body axis system is a system which x direction sits on the chord line of the aircraft. Essentially sits on the point, on the line that connects center of gravity and nose of the aircraft. So this is called a body axis system. And we can draw the other axis, y of b, which is going to be 90 degrees, and z of b, that is going to again be 90 degrees. So Earth axis system is going to be on the surface of the Earth. Then you take it to an altitude. It is going to give you the moving Earth axis system, and then you rotate it to align with the line that connects the center of gravity and the nose of the aircraft. The next one is the air path axis system. What do you think this one is?
X-axis is where your forward velocity is.
Exactly. So your x-axis is going to point towards the direction of the air flight path, essentially the direction of the air movement. Then you have z of, this can be called x of a, z of a, and y of a. So air path axis system uses the symbol a, subscript a, x of a. Body axis system uses the subscript b, and the moving Earth axis system uses the subscript e. And a regular Earth axis system uses subscript g. So based on these axis systems, we are going to define 9 angles. First one is angle of yaw. What do you think this angle of yaw is? It is pretty self-explanatory, right? Yes.
It's the angle that your plane is like up. Is it up from here?
What is the direction of yaw?
Left and right.
In this direction, right? So that it should be an angle that characterizes this movement. Do we know the main movements of aircraft? Roll, pitch, yaw, right? Pitch is going to be upward, moving up, ascent or descent, right? And then we have roll, we have yaw. right? We talked about this in lab 1 a little bit. So based on this, we can define this angle of yaw, and I'm going to write the definitions for you as the angle between the projection of XP axis, this axis, on XE, YE plane. I'm going to draw this for you. And the XA axis. Angle of yaw. XE axis, I'm sorry. So, this is going to be your XB. Again, let me draw this. This is going to be your XB. And we have the E direction, XE, YE, and ZE, right? On the other direction. So the projection of this XB on this plane the projection of this on this plane, let's call this projection, let's say this projection is this, x of b prime. The angle of this projection and x of e. So this is called angle of yaw, psi. Yes. PSI, psi. Next angle. Angle of pitch. Theta. How do you think we define the angle of pitch? Yes.
Is it the projection of ZB onto Z?
Projection of ZB
So
onto
onto the ZE and the Y for the.
so you mean this angle, right?
Yeah, that angle right there.
That's it, which is true. But we can also define it as the angle this XB makes with this XE YE plane, right? This angle. Same thing, right? So, angle of pitch. How much you have deviated, how much your plane has deviated from the earth, that plane that lies on top of the surface of the earth, like at an elevation, of course, but it's the parallel to the surface of the earth. Again, XE, let's say this is your XE and YE. Surface of the earth has the same plate, so these two are going to be parallel. And X of B is going to be this angle. You can make the same argument as, what was your name?
Jackson.
As Jackson made. It's going to be the same angle. Of course, the direction may be different. That's why we use the plate, not this XE. So this XB can move a little bit, right? Because you just make sure that we are talking about the angle of this with this plate, not one of the axes. Okay, next one. Angle of roll. How do we find the angle of roll? I guess you understand the team right now. The team is, we are talking about the XE and YE and ZE, which is the coordinate system that is in the same direction as the coordinate system on the surface of the earth. Just move to an elevation, right? Move to an altitude. And the coordinate system that lies in the direction of the plane. XB, let's say YB, and ZB, right? So you get it. These three angles so far have talked about the relationship between these two coordinate systems. Based on this, how do we define the angle of roll? The angle of roll. So we are rotating in the direction of the y direction, in this direction, right? It is officially defined as the angle between YB axis, so this axis, and this is a doozy, intersecting line of YBZB plane and the XE ZYE plane. So we have this plane. Let me use a different color. Maybe a different. We have this XE YE plane. And then we have ZB and YB plane. ZB, YB. They are going to intersect at a line. Let's call this is your line. And the angle between these two is going to be angle phi, a small phi. Angle of roll. This is a very complex definition of angle of roll. Just have to keep in mind that how much your airplane has rotated, right? But this angle of roll also this specific angle of roll definition also includes the moving in the curve. Let's say you are rolling, right? But you are also moving on a curved path, right? That angle, this angle with the horizontal plane, this angle, I don't know how to show this without a proper plane, but this angle is essentially your angle phi, right? The definition is a little complicated, but I hope you understand what it is. How much you have rolled, right? How much your aircraft has rotated on the y-axis, on the x-axis, right? Does it make sense? Yes? A little. Where is the confusion? Just don't look at the definitions. How would you characterize the angle of pitch for yourself on a two-dimensional panel? This is going to be this angle of pitch, right? You have an axis compared to which is parallel to the Earth's surface, and how much you deviate from that axis in this direction is going to be the angle of pitch, right? Angle of yaw, let's say we are looking at it from the, again, two-dimensional is going to be much easier to understand. Let's say this is the original axis, and this is the direction of the flight. This is going to be angle of yaw, right? Angle of roll, front view of aircraft, horizon, angle of roll, phi. On a two-dimensional plane, but on a three-dimensional plane is going to be a little harder to grasp, okay? The problem with this angle of roll is that your airplane itself may not, will not actually move. Let's look at it from the front view, will not move on a line. So it will not move toward the outside of this tablet, right? It will move on a curve. And that curve is also included in the angle of roll. That's why we defined another angle that only looks at this angle. And that angle is called the angle of bank. Angle of bank is shown with the capital letter phi. Which is essentially defined as the angle between YB and its projection on XE-YE plane. YB and YB's projection. This is a little easier to comprehend on a three-dimensional plane. So we have a projection of this YB on this plane, which let's say this is the projection, right? This angle is going to be the angle of bank. YB is in this direction. You have that plane. You make a projection of YB on that plane. The angle between the two is going to be the angle of the bank. So 4 angles that only relate to the position of the body of the aircraft: angle of roll, angle of pitch, angle of yaw, and angle of bank. I just want to go back to this because we have a couple of mechanical engineers in our meet, and I didn't notice. I want to make sure that we understand what roll, pitch, and yaw of the aircraft is. Yes? Is there anyone who doesn't know what roll, pitch, and yaw is? You guys know? Yes. Okay. Okay. Move on to the next 3 angles. These ones talk about the angles between the XB system, XA system, XA, YA, ZA, and the XE, YE, and ZE. So air path and the moving earth. So essentially these angles are going to talk about how air is moving with respect to earth, or how air's movement is situated. Let's put it this way. Air's movement is situated. These are going to be very rarely used, but it's just an introduction, so we just have to become familiar with it. First one is called the azimuth angle. And it's shown then with capital letter X. So movement of Earth, let's say air is moving in this direction. And you have the Earth right here. Again, one of the problems we are having here to understand these angles is that I'm writing on a 2-dimensional board, but I'm trying to explain a 3-dimensional axis system, right? So keep that in mind. So we're going to have XA, YA, and ZA, right? The movement of Earth. We are going to have XE, YE, and ZE. The angle, let me change this a little bit. ZE. YA. So we're going to find the angles between these 2 coordinate systems. These are the angles. What is the azimuth angle? It is the angle between the projection of XA on the XEYE plane. So angle between this and the XE axis. So XA and XEYE. You project this on XE and YE plane. Let's call it XA prime. This angle is going to be your azimuth angle. Does it make sense? So essentially, it is the same thing as the angle of yaw. The difference is going to be that this is on an airframe axis. And you're gonna see this trend over and over again. The same one is the next one, I'm sorry. This next one is the flight path angle. Which is I made one small mistake. This is also a mistake in the notes. Make sure to fix this. I will also fix it. If you have downloaded the notes, make sure. Okay, this is the projection between x, let's see, YZ axis. YZ axis. So this angle is actually this angle. Sorry guys, it is Z. This is the YZ plane. You project this X of A on the YZ plane. This will be your azimuth angle. Flight path angle, on the other hand, has the previous definition. So it's going to be the angle between the projection of XA, going to use this color, on XEYE, and so you project it on the XEYE plane, and then the angle between the projection and the axis itself is the flight path angle, shown in green. Next one is the aerodynamic angle of roll. Which is going to give B the angle between, I'm going to use orange to use this angle, the angle between YA axis and again the intersecting lines of YZ, YAZA plane and XEYE plane. So there's a line here, which essentially means that this will be your angle. This is X of E. Let's say this is Y of A. This will be your angle, aerodynamic angle of roll, mu. These are the same angles as the angles of yaw, roll, and pitch, but in a different coordinate system. I understand this is a little confusing, so if you are confused, you just have to go back to the definitions and try to figure them out. But as long as you understand the angles roughly, you should be fine. You don't really need to memorize the definitions. The next ones, which are the angles that are used the most, is the angle of attack. The first one. How do we define angle of attack? What do we think? Based on these 4 different coordinate systems, how do we define the angle of attack? Yes?
It's the relation of the air path system to the plane like bodies.
So exactly. So we had the XB, YB, ZB, right? The body axis. And we had the XA, YA, ZA, the air path axis. So this angle is then going to give us the relationship between the angle between x of b and x of a. So this is your plane. This will be your x of a, right? Let's say this is the direction of air. So, I'm sorry, this is x of b. It's going to be x of a. This alpha angle of attack is the angle between x of b and x of a. Pretty simple. The next thing that you haven't seen in aerodynamics because you were only dealing with two-dimensional flights is called the angle of side slip. In some book, this is also called the bank angle, which is different from the angle of bank we had before. But we are only going to call it angle of the side slip, beta. Angle of the side slip is the angle between XA and the plane of symmetry of aircraft. This comes into play when you have a wind gust, right? So essentially the direction of the air is going to be different than the plane of the symmetry of the aircraft. Let's have a top view of it. This is a top view of the aircraft. Let's say you are moving in this direction. This will be x of A and x of B. We are looking at it from top. So in general, if you don't have a wind gust, this is how it should look like. But when you have the side shift, when you have wind gust, your x of A is going to be in a different direction. Does it make sense? This angle is going to be angle beta. This is where a lot of your stability, if you end up, I mean, I'm pretty sure you will, if you take AESP 460, flight dynamics and control, they will have a discussion on stability of the aircraft, right? Wind gust is one of the main force sources of instability, right? So when your air path is different from the movement of the aircraft itself, you are going to see the angle of side shift. Any questions? Okay. So, let me ask you this. How confident you are in the understanding of these angles? We have one person who is fairly confident, one person who is not confident. Where is the question? How many of you are very confident? Just one. That's good for you. 3 people. Let's see one person who's, where's the confusion?
I'm gonna need to look at it somewhere.
Okay.
In the book and stuff.
Pardon me?
Gotta see it better in a 3D space for some.
Yeah, it is a 3D thing, so it is a little hard to conceptualize a 3-dimensional thing in a 2-dimensional setting, which is our board. But I guess we can do one review of it from the beginning, and then we'll move forward. So those of you who are a little more confident, please help me here. What was the angle of yaw? Let's say I have this aircraft. Angle of yaw. And I'm going to give you a 2-dimensional representation of the whole thing. So let's say this is my aircraft, right? And this is XE. So XB, XB. And since I'm looking at the top of it, I'm essentially looking at the projection of XB on the XEYE plane, right? So I'm already looking at the projection, right? That projection made things complicated. How would you define angle of yaw here? The angle between these two, right? Psi. And then this is a top view again. I want to make this a little less complicated. That's why we're looking at the different views. Let's have a side view. And when I say side view, we are dealing with the projections. We are essentially projecting the axis on a plane, right? We are making things two-dimensional to make things simple. Again, this is x of E. This is your x of B. The side view angle, it's a projection on a different plane. I mean, it's not a projection, it's the axis itself. And the angle of pitch is going to be this angle theta, right? Okay, let's have a front view of it. This is your aircraft. It is rolling. It's going to look like this. This is your y of E. And this is your y of B. Yes.
So on the side view, does the plane going towards the XB direction and
Yes, it is not going. It is direct. It is situated in that direction, right? It may be going this way, but you may have this pitch, right? We are not talking about the direction of the movement of the aircraft right now. We are only talking about the location of the body. Whenever you are talking about the B coordinate system, you are talking about the location of the body. And x of E, all of the subscript E are talking about the surface of the Earth, right? Parallel to the surface of the Earth. So this one, this is the angle of bank, the capital phi, right? The small phi is a little more complicated, and it is not possible for me to show it in a two-dimensional setting because it is also including the turn of the aircraft, right? So if I had to show that on this two-dimensional thing, then we would have, let's say your aircraft has turned this much, then this angle would be the small phi, angle of the roll, right? To make it simpler, we have come up with the angle of bank. Is this more understandable? Okay. Let's move on to the next one. Then we have the azimuth angle. Again, you come here, instead of the top view, instead of the aircraft, we are going to have the movement of air. Let's say this is the direction of the movement of air. Let me actually try to. This is the direction of movement of air. So x of A. And then this is x of E. Again, top view. This is going to be your azimuth angle. Flight path angle. Direction of the Earth. This is also a side view. Direction of the Earth, or horizon, whatever you call it. Direction of the movement of the Earth. Flight path angle. This is much more common. Flight path. We don't really use the azimuth angle that much, but the flight path angle is very also a pitch angle of pitch, right? You have to be careful that the flight path angle is defined as the angle of the movement of air with respect to the horizon, right? It doesn't have anything to do with the situation of the aircraft itself, right? Aircraft is defined by the angle of pitch. And then we have the next one. What was the next one? Aerodynamic angle of roll. So for aerodynamic angle of roll, you have y of E again. Then let's say your air is in this direction. This is going to be your aerodynamic angle of roll. And what was mu? Mu. Is this a little more clear now? Okay. And I assume hopefully you understand the angle of attack as you have passed aerodynamics. Angle of attack is the angle between x of, this is a side view, x of b and x of a, alpha. And we talked about the angle of sideship. When the x of b has an angle, the project from the top view, x of b is going to be in this direction, top view. And x of a will be in this direction. Beta, angle of sideship. How do we feel about these angles now? Who is more confident? Show of hands. Okay, that's a good number. That works for me. But we have some confused people still, which I assume is going to be fixed when you go back home and study a little bit. So let's talk about the velocity components. We understand the angles. We can find the velocity components for each directions. Velocity components, we have v, capital V is your velocity vector squared, which is equals to a small v, a small u plus, and this is we already know this. The vector is ui vj k wk, right? You want to find the magnitude is going to be v squared equals to u squared plus v squared plus w squared. But how can we find the components of it? U is defined as v. These are only magnitudes. Cosine of angle of sideship, cosine of angle of attack. V is defined as v sine of angle of sideship. And this is a small v. This one, small v. And W is defined as V cosine of beta, this angle of sideship, plus sine of alpha. And again, these U, V, and W are your projections of velocity vector on xb, yb, zb. So your body axis, on the body, directions of the body. These are the velocity components. That's how we define them. But let's say, let me ask you this question. Let's say we have a two-dimensional flight. This is the direction of velocity. You have x of b and z of b, right? And y of b is coming out of the page, or coming out of the board. What will be the components of velocity here? How would you simplify the components of velocity for this flight? What can you say about the angles? Angle of attack and angle of sideship.
There's no angle of side.
Angle of sideship is 0, which means that the velocity in the YB direction that is coming out of this page, coming out of the board, is 0, right? And the rest of it is just a regular two-dimensional projection. Does this make sense? Okay. We can have the same analysis for the angular velocity. We define the angular velocity, the vector, as pi plus qj plus rk. So the components of this angular velocity in different directions. How do we find these? This is going to be, again, since we are talking about the angular velocity, so we are going to be interested in the changes in angles. P is going to be the changes of psi. What was psi? Angle of yaw, exactly. So P, this x component of your angular velocity, is going to be the changes in psi in time multiplied by sine of theta plus d phi, this is a small phi, angle of roll, with dt. Q can be the other component, can be defined as d psi dt cosine of theta sine of phi plus d theta dt cosine of, cosine of phi. And R can be defined as d psi dt cosine of theta cosine of phi minus d theta dt sine of phi. We can rewrite this and find the d psi and d theta dt. The changes are in the angle of yaw and angle of pitch as a function of these components of moment. Angular velocities, I'm sorry, not moment, angular velocity. We don't have that much time left. So at this point, let's think about why are we defining this? What is the use? What do you think we are doing? Why do you think we are doing this? Any ideas? As it's a lot of theory, confusing three-dimensional theory. Who cares about this, right? Yes.
If you know the angles, then you can get the components and therefore the velocity for velocity and velocity.
Velocity. That's a very good observation. Yeah, but I mean, at the end of it, what do we want to understand?
How to control an aircraft.
How to control an aircraft. And what contributes to this control of an aircraft? Or essentially how to design a control system, right? Because the pilot doesn't really cares about these components. How to design a control system. Yeah, sure.
Well, we're finding velocity and acceleration here, and we know, as far as the flight control systems part, how fast the aircraft can go, how fast it can accelerate, what the limits of that might be.
Exactly. So essentially, based on, what was your name? Max, and you're Jackson. I always confuse. Jackson, right? Okay. Confuse the two of you. Okay. No. I know you. I forgot your name though. Okay, I'm sorry. But so the idea here is that to understand all of these angles, understand all of these velocities, to eventually have an idea of the forces acting on the plane. When you understand the forces acting on the plane, which essentially means that when you can write the equation of motion, you can understand the motion of the aircraft and forces needed for a specific velocity, right? How much thrust do I need for this aircraft to fly at this velocity in cruise, right? In cruise conditions. We need to know all of this. We are going to simplify them to get to simpler solutions, but in general, if you go to a propulsion company, work on the thrust of engines, these part of it are going to be taken care of by a computer. But understanding how things are fed to a computer is not a bad idea, right? As an engineer, as an aerospace engineer. So I understand it is confusing. It may get a little boring, but we are building up to something. So bear with me, okay? I guess that's it. We are at 11:19. So that's it for today's class. See you on Thursday.